Hi, welcome back. Hello. Hi, everyone. They're waving. Studio audience is waving at me. Hello. Hello. So we're doing two items today, two sections. We're doing 7-3 similar triangles and 7-4 parallel lines and proportional parts. Let's kick it off with similar triangles. We are solving problems with similar triangles, and we're going to do that by identifying those similarity postulates and theorems. We will be using proportionality from the previous section. First off, we got to figure out what's a similar triangle. So if we recall from previous section, a similar triangle is going to be exactly like a similar polygon. It's a triangle where all three angles are congruent and all the sides are in proportion. That is, when I write a fraction, those fractions are all equal to each other. Our first postulate to help us decide if triangles are similar, though, is a shortcut, and it's postulate 7.1, the angle-angle similarity postulate. And what this says is that if I have two angles in one triangle congruent to two angles in some other triangle, then that's all I need to say that the triangles are similar. Now, this is a postulate, so I'm not going to prove it to you. I'm just going to ask you to please take my word for it and go, yes, boss. If you say so, I only need two angles in order to say that the two triangles are similar. So what I'm looking for is a setup that looks something like this. Two triangles where two pairs of angles are congruent to two other pairs of angles. If so, I can state that they're similar. Let's remind ourselves how to write the similarity statement for this setup. I'm going to write the name of the first shape, which is triangle ABC. The order you write these letters in for the first shape, unimportant. The similarity symbol, which is like an S that fell down. And then because the second shape is a triangle, I'm going to write the symbol for triangle. And now order is important. So my first shape, I wrote the letter A first, so I need to write the corner that corresponds to A. A has one arc, so as I look at my second triangle, I'm going to find the corner with one arc. Here it is F, so that means I need to write the letter F first. In my first shape, I wrote the letter B next. B has two arcs, and in my second shape, the E has two marks. So E is going to be the next letter, and then D will be the following. Questions on how we write that similarity statement? Seems familiar? You remember from last time? Cool. Let's go ahead and look at example 1, and this is exactly how you're going to do items 1 through 4. So I'm going to write up here in my notes that this goes for skill practice questions 1 through 4. You're welcome to write on your skill practice that this is notes 7-3, example 1. Let's look at letter A. I'm looking at letter A. I see two triangles, so they're the same shape. I'm going to try to find congruent angles. I see this angle here at L is 57 degrees, and this angle at M is also 57 degrees. I have J at 48 degrees, and I don't have 48 degrees listed anywhere else. And in fact, this angle is missing a letter. So studio audience, can you give me what letter you want me to name this corner? O? Okay, I'll go with O. O sounds good. All right, so I don't have an angle measure for K, and I don't have a measure angle for O. So I need to find either the measure for K, which could help me decide if it's congruent to P or not, or I need to find the measure for O, which will help me decide if it's congruent to J or not. Let's go ahead and find the measure for angle. Yes, sir. Yep, go ahead. Let's go ahead and find the measure for angle K. All right, as I look at this triangle, what do I remember about the angles in a triangle? They add up to 180 degrees. So if I'm trying to find the measure of angle K, I can take 180 and subtract off those two angles that I know. As I write down that that's what I'm doing, can I get you guys with your calculators to give me what that's going to be when we do 180 minus 57 minus 48? $70? 57. $75. And I heard a couple other voices say 75 also, so we confirmed. Okay, so angle K is 75 degrees. All right, if I look at my second triangle, I have a 75 right there. That means K and P are congruent, so they are corresponding. And that means that J and O end up having to be congruent because, well, if this is 75, that one's 75, which means that one has to be 48. Okay, so we have enough to state that these triangles are similar. The reason I can say these triangles are similar are by postulate 7.1. That is angle-angle similarity. I have two angles that I can see are congruent to each other. The yellow angles are congruent and the blue angles are congruent. All right, I'm going to write my similarity statements. I'm going to write the first triangle, that's the triangle on the left, those letters in any order. And now I'm going to write the second triangle, the triangle on the right, in the same order as the first triangle. So I wrote the yellow corner first, then I wrote the green corner, and then I wrote the blue corner. Yo, this triangle's name is Mop. Easy enough? When given angle measures, yeah, this is totally easy, but look at example B. There's no angle measures. This one is a little more challenging. I'm going to zoom in a little more closely so that we can take a better look at it. All right. As I'm looking at these two triangles, I have this small one here on the left and I have this slightly larger one here on the right. What things do I notice? Rx and TW are parallel to each other. Awesome. Okay, since they're parallel, what kind of information does that give me? Okay, RW and XT are transversals. These are lines that intersect parallel lines. I'm only going to mark RW so it doesn't get too messy, but that means that this angle here at R and this angle here at W have a special relationship. Do you remember what that name of that relationship was? What was it again? He said opposite interior angles. We're going to clarify the terminology the book uses is alternate interior. It means the same thing. They're on opposite sides of that transversal. So I got what you were saying. All right, so we have some alternate interior angles happening here. And by our alternate interior angle theorem, what do we know about the measures of these alternate interior angles? Huh? No, sorry, go ahead.
Oh, no, it's checking it out.
Oh, okay. So by the theorem, what do we know is true about the measures of these alternate interior angles? They're congruent. Awesome. So because they're alternate interior angles, I can state that the angle at R, yeah, I'm just going to write the angle at R is congruent to the angle at W. All right. I have one pair of angles congruent. I need at least one other pair of angles congruent to make this work. Yes, ma'am. All right, she's saying angle TSW and angle RSX are vertical angles. I have two lines here, RW and XT, intersecting at this one point here at S, which indeed makes these angles on either side of that little intersection vertical angles. And by the vertical angle theorem, those angles are congruent. Very good. So she said angle RSX and angle TSW. All right, do we have enough information to say these triangles are similar? Yes, because my postulate 7.1 said I only needed to show two pairs of angles congruent in order to state these triangles are similar. Now we do have to be careful about writing these in the same order. And notice how here we had R congruent to W. So those are the two that are corresponding. And so I wrote those two first. And then here I wrote that angle S was congruent to angle S. So we had the same letter. All right, questions? Cool. We have two theorems when it comes to triangle similarity, two other ways that we can show triangles are similar, so we don't have to just rely on the angles. We can use things that feel similar, that feel familiar from our triangle congruence days. The first theorem for triangle similarity that we have is side, side, side. It says that if I have all three pairs of sides of two triangles proportional to each other, not congruent, proportional. That means when I write the fractions comparing them, those fractions are going to be equal. If I have all three pairs of sides proportional between two triangles, then the triangles are similar. The next theorem is side angle side. It says if I have the lengths of two sides of a triangle, bless you, in proportion, and the included angle, that is the angle that's created by those two sides that I'm looking at, congruent angles, they're congruent, then that's enough information for me to say that the triangles are similar. Okay, so this should feel very much like triangle congruence, but we're showing similarity. And the difference between congruence and similarity is congruence, the sides had to be equal measure. Now, the sides are just in proportion. That is, when I write a fraction comparing the sides, I'm going to get the same fraction every time. Let's practice using these. Let's do example A. The directions state, determine whether the triangles are similar. If so, write the similarity statement. Explain your reasoning. Explain your reasoning is using either the postulate 7.1, angle postulate, or the two theorems we just talked about, side, side, side similarity, or side angle side similarity. Okay. Looking at A, do I have any information about angles in A? Let me just zoom in a little bit more. I mean, nothing explicitly stated, right? I don't have any numbers. So I'm going to go ahead and use side measurements because I've got a bunch of side measurements. So let's figure out which sides are corresponding just to help me out here. To know which sides are corresponding, I'm going to go with their measurements. I'm going to correspond the smallest sides to each other, the largest sides to each other, and the medium sides to each other. 5 is the smallest side here. 12.5 is the smallest side here. 8 is the medium, 20 is the medium, and 6 is the biggest, and 15 is the biggest. That is biggest and smallest within their own triangle, not overall between both shapes. So the goal is I'm going to write a fraction comparing the small sides together. And I'm going to look at what that fraction is. And then I'm going to do another fraction and I'm going to compare the medium sides together. And I'm going to do a third fraction and I'm going to compare the long sides together. And what I'm hoping for is that all the fractions are the same. Say that again. Huh? What? No? Yeah, that's okay. Yes. Yes. Okay. All right. So I'm going to put the triangle that's on top in the numerator and the triangle that's on the bottom in the denominator. Triangle on top in the numerator, triangle on bottom in the denominator. Do I always have to put the triangle on top in the numerator? No, if I really didn't want to, I didn't have to. But once I've decided which triangle goes in numerator or denominator, I have to use that same pattern for all the other fractions. Otherwise, I'm going to mess something up. All right, I don't know how to reduce 5 over 12 I don't know how to reduce 5 divided by 12.5. So I'm just going to use my calculator. And I'm going to get myself some decimals. So 5 divided by 12.5 is 0.4. You guys want to help me out with the other fractions? Point 0.4 again on 8 divided by 20. Okay, and then 6 divided by 15. Also 0.5. Oh, 0.4 also. Okay, cool. All three of these have the same fraction. This means that their sides are all proportional to each other. And so I can state that these triangles are similar. Here's the triangle on top, triangle PQR is similar to triangle. Now I need to name this bottom one. P was the point between the blue and the green lines. So S is going to go first. And then the second letter between blue and yellow, T, okay. And the third letter? R, all right. And now we need to explain the reason. I checked all three sides being proportional. What was that name of the theorem that used all three sides? Postulate 7.1 was angle, angle. Required angles, we didn't use angles, which is the one that used all three sides. Side, 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 similarity theorem 7.2. Good job. You're welcome to use either the number or the name. I'm going to highly recommend that you use both. So that way, when you have to do any more explain or proof, you've got those in your head. Not too hard, right? Okay. Let's do B, because B looks kind of crazy. Like, there's only one triangle there. There's a triangle with a line. No, we got two triangles. We got the small one on the top, the triangle AEF, and then we've got the big triangle that's sticking out from underneath it, ACB. I don't know anything about this side here, CB, and I don't know anything about this side, EF. So I'm missing information on one pair of sides. There's no way I can use theorem 7.2, the side similarity. But I do have this angle here at A being shared. And since A is being shared both with the small triangle and the larger triangle, I can say that it's congruent to itself. Do you remember what property allows me to say that a thing is congruent to itself? Shout it out as soon as you know. Yeah, the reflexive property. Nicely done. Good memory. Or rather, good guessing playing a Wheel of Fortune. The reflexive property lets you say a thing is congruent to itself. All right, so now I just need to get the sides. All right, I'm gonna show this side as a fraction with this longer side. And I'm gonna do this side in a fraction with this longer side. All right, I'm gonna do the yellows first. The short side is 8. The longer side is 8 plus 4. What's 8 plus 4? 12. Why did I do 8 plus 4? Yeah, because the small triangle is sitting on top of the big triangle. And so that side from AC has AE as part of it, and it just continues to go on to C. Yeah, that's what you were saying. Yeah. All right. I can reduce this down in my head. 8 and 12 are both divisible by 4. 8 divided by 4 is 2. 12 divided by 4 is 3. So my fraction there is 2/3. All right, let's check this other one. So I'm going to have the 10 in the numerator, and I'm going to have 15 in the denominator. You agree with me on the 15? Yeah, 10 plus 5. Okay. 10 and 15 are both divisible by 5. 10 divided by 5 is 2. 15 divided by 5 is 3. The fractions are equal. That means they're in proportion, and so I can say these triangles are similar. How did I get 15? 10 plus 15. Or excuse me, 10 plus 5. The same reason why I got 12 over here, I did 8 and 4, because I had to walk 8 and then 4 more. I did the same thing here. I had to walk 10 and then 5 more. Yeah, I was looking for what divides both 10 and 15 equally, and I found that 5 divides them both. 10 divided by 5 is 2, 15 divided by 5 is 3. Now I have to write the reason. I got an angle congruent to each other, and now I've got the two sides on either side of the angle, which means this is my theorem 7.3, which is the side angle side similarity. Questions? We're all right? Okay, gonna zoom out a little bit. All right, let's go figure out which ones these are like. The directions say determine if they're similar. So I'm gonna look into 7.3. Yeah, I think 1 through 8 could use all of these. Probably more like 5 through 8. So we'll just call these 1 through 8. You can use some of this information. Now we've got some more theorems. We've got the properties of similarity. Properties of similarity should be real familiar. We have the reflexive property, the symmetric property, and the transitive property. These work exactly the way we're used to them working, but now they're for similar things. So if I know I have a triangle, I can say it's similar to itself. If I have two triangles that are similar, then it doesn't matter what order I write them in around the similarity symbol. And if I have one triangle similar to some other triangle, and that triangle is similar to some other third triangle, then the first and third triangles are similar to each other. Now, again, the hardest thing, the only way I have of making this hard is to throw some algebra at you. And so example 4, which will help you with, I think, 5 through 8, because there's some algebra there. Ask you to use parts of similar triangles. So as I'm looking at these two triangles, this short one and this bigger one, I can use the fact that they're similar to help me kind of say some things. All right, I want to find BE. BE is this one. So I want to find the side that corresponds to that particular side, which is going to be this one. All right, I'm going to set them up in proportion with two other sides of my other triangle. So I'm going to pick this one and then this long one, A to C. The reason I'm picking these two sides is because they have numbers. If I tried to pick the other ones, the A through E, I'd have another variable and that would not be helpful. All right, so I'm going to write a proportion with side AB over AC equal to side BE, which is the one I'm interested in, over side CD. All right, let's see, AB is 3, AC is 5, BE is X, and CD is 3.5. This now should feel very similar from what we did in section 7.1. So I'll refer you back to section 7.1 to remember how to cross multiply and divide. I'll take some questions on how I did this setup while I quickly write down the kind of the first starting things of what I should do for this. Questions so far on similar triangles? Chat looks quiet. The classroom is quiet. Okay, I know this is pretty simple when I give you just kind of numbers like this. To just throw this in your calculator, do some multiplication, do some division, and call it a day. But please show all of your work in terms of setting up your proportions, in terms of showing that you're doing that cross multiply before you do the divide. Cool. Glance in here, we've got some challenge questions. I'm going to let you chew on those on your own. Let's jump into note 7.4. In 7.4, again, we're solving problems, but we're going to be using the properties of parallel lines and proportional parts. Again, triangles come into play, and again, it's proportion. So again, we have fraction equal fraction. Let's look at our first theorem for this section. Our first theorem is called the triangle proportionality theorem, and what it says is this. If you have a line inside of a triangle parallel to one of the sides of the triangles, and this parallel line is crashing into the other two sides of your triangle, then this parallel line is going to cut these sides of our triangle into proportional pieces. That means that these two short pieces written as a fraction to these longer pieces, those fractions are going to be equal. Okay. So we're going to have some equal fractions, and we're just going to show you that color coding here real quick to help you see it. So the pieces that it got cut to of one line in one fraction, and then the pieces from the other line that got cut in the other fraction. If you write the short piece in the numerator, then the other fraction has to have the short piece in the numerator. Okay, let's practice this in example 1. All right, in triangle PQR, these two lines are parallel. This shape here means parallel. Okay, STQR parallel. That means that I've got some proportional parts that happen. So I have this piece creates a fraction with this piece. And this piece creates a fraction with this other piece, and those fractions are equal. All right, let's go try to find that information in the word problem so that we know where we put things. Okay, PS is the find. Awesome. It's going to be in a fraction with this piece SR. Okay, I have numbers. That's good. That's good. That means I can do some stuff. PT, here it is. Okay, so we have some more information. Hang on, my computer decided to freak out. It's thinking, and it's back. Hi, thank you for the brain break, computer. And it's in fraction with this other piece, TQ. All right, there it is. And I'm going to fill in what they gave me. I don't know what PS is, so I'm going to use a variable. There's the pink information. There's the blue information. There's the red information. And once again, this now looks like a setup from 7.1, cross multiply and solve. While I jot down the algebra, do we have any questions on how I did this setup and use this triangle proportionality theorem? Check in the chat. Check in the classroom for hands raised. I don't see anything. So I assume everyone feels okay with me getting an answer of 6.25. Okay, I'm gonna go check in your skill practice to see which questions this helps with. Yes, sir. Yep. This is gonna be 1 and 2. Just like that one. The only way I have of making this harder is to give you weirder algebra things. Now, this theorem that we just talked about, it has a converse. It means we can come at it from the opposite direction. The original direction said, if I know the thing is parallel, then I can say I have a proportion. What the converse says is, if I have a proportion, then I can say lines are parallel. So this is the theorem that you're going to use as justification to state that you have parallel lines. So to use theorem 7.6, you need to not know lines are parallel, but be able to check for proportion. To use theorem 7.5, you have to already know lines are parallel and be wanting to calculate proportions. Example 2 is what you're going to be doing in questions 3 and 4. 3 and 4? 3 through 5. 3 through 5. In questions 3 through 5, you're going to be asked, are these lines parallel? Yes or no? And likely, you're going to have to explain your reason. Let's look at the information they've given us so far. They've told us that in triangle DEF, E to H is 3, H to F is 9, and DG is 1/3 the length of GF. That doesn't seem helpful. Okay, let's write in math statements the information that we have so far. If these are parallel, then I should be able to write this as a fraction, and I should be able to write these as a fraction and be able to show somehow that those fractions are equal. If I can do that, I can say that these lines that I'm interested in are parallel. Okay, let's do this side first that has numbers, because that's the easiest thing for me to deal with. So I'm going to write line EH and line HF as a fraction. Again, it doesn't matter which way you write these fractions, just write them. Okay, EH is 3, HF is 9. If I reduce that down to simplest terms, I'm going to get a fraction of 1/3. All right, there's blue information. I'm going to write this out as an equation in math and see if I can monkey around with it to see if I can get something that looks like this. EH over HF is 1/3. If I can do that, I've won the internet and I've shown that these lines are parallel. Okay, time for me to translate this sentence. DG is, I'm going to use the equal sign, that means is, 1/3 the length of means multiplication, GF. All right, so I have DG equals 1/3 times GF. Well, if I look at this one here, which is what I want it to look like, I see I have the 1/3 by itself. So I'm going to try to get the 1/3 by itself over here on this left-hand equation. Because if I can do that, then maybe I've done it. How do I get the 1/3 by itself? What's happening to 1/3 right here? It's being multiplied. So how do you undo multiplication? Divide. I'm going to divide by GF because that's what I'm trying to get rid of in order to get the 1/3 by itself. What I do to one side, I have to do to the other. These GFs are going to cancel, which on the right-hand side leaves me with the 1/3, which is what I was after. And on the left, I now have the fraction DG over GF. Is that the same kind of corresponding sides that I have here on my triangle? Yeah, I have short over long, which is basically the setup I have here with EH over HF. And because these fractions are the same, those sides are proportional. And since those sides are in proportion, yes, these sides are parallel. That's the hardest thing I can do to this. Okay, you've got 3 questions to try it out on. Make a mess, come see me if you need help. How are we doing? How are we feeling? We're okay? We're doing good so far? No one's fallen asleep too badly yet, have you? Maybe a little bit. If someone near you is falling asleep, take a moment and kind of gently tap them. Oh, gently tap them. Yeah, wake up. You okay? Are you all right? Do you need a mental health day today? You'll watch the playback later? You'll watch the playback later? Okay. I trust you that you will take your mental day. Okay. How are you doing, baby? Don't come too close. I got camera on. Yes, as soon as we're done here, the answer is yes. All right, let's get the last section done. Let's get the last section done, mid-segment. On the chapter 6 quiz, there was a couple questions talking about the median. And I had several of you come up and go, what's median? There was a little tiny section of the notes, like really small, that I didn't read and I didn't say out loud, that said that another name for mid-segment of trapezoid was median. I'm so sorry that I didn't read that out loud. Median, when we're talking about triangles, goes from vertex to midpoint. Mid-segment goes midpoint to midpoint. So in a trapezoid, a median goes midpoint to midpoint. It's the same as mid-segment. In a triangle, mid-segment and median are 2 different things. Okay? But the good news is that the mid-segment of triangles is like really similar to mid-segment of trapezoid. If you recall, mid-segment of trapezoid said that the mid-segment was the average of the 2 bases. You added the 2 bases up, you divided it by 2, that gave you mid-segment. In a triangle, it's basically the exact same thing, except We only have one base. So just take that one side, divide it in two. That's the measure of the mid-segment. Lickety split, you done. The hard part about this, and we're going to glance in here, it's looking at 6 through 8. The hard part about this is that these figures look like this hot mess. And you have to figure out which segment goes with which side. All right, let's do A. A wants us to get information on XZ. Okay, XZ is this one right here, which you can't really see very well, so I'm going to highlight. Is this one right here. I want the side that is not touching that one. According to Theorem 7.7, this measurement here is half of this. So XZ is 1/2 of 13. You cannot read that. That was a very bad, poor choice of colors. Let me try again. 13 divided by 2. You can leave it out as a fraction. That makes me happy. You can turn it into decimal. I'd be meh about it. I know you can think through ST. We'll highlight real quick. Here's ST. It's related to a mid-segment that's not touching. That's this one. Now this time I know the mid-segment. I was told the mid-segment is 7. But the mid-segment 7 is half of this side that I'm interested in. What is 7 half of? 14. You did 7 times 2. Or thought, what divided by 2 gives me 7? Very nice. Let's erase some of this mess because it's messy. All right, to try to find the measure of angle RYX. RYX, that's this angle right here. It lives along this base and this mid-segment. Now our theorem also tells us that that mid-segment is going to be parallel to the side of the triangle that it's not touching. So what's parallel to this side here is the mid-segment, this one right here. And now we have some alternate interior angles happening. As discussed earlier, alternate interior angles are congruent, I heard. So this is the same as that angle measure that I was given. Questions? We're okay? All right, last section. Let me see which questions it is. This is questions 9 and 10. 9 and 10 uses these 2 corollaries. A corollary is some statement that you can make that immediately follows from some other information you've been given, usually a postulate or a theorem. So something like this. We know, we're going to pretend that we've got a theorem. Theorem, Dr. Carranza has a YouTube channel. Corollary, she's kind of cool. Maybe, right? She tells lame jokes. Corollary, maybe she's a parent. She tries them out on her child. When he goes, Mom, that's a good one to use. Okay, that's a corollary. Some statement that falls out of something that we already know. 2 corollaries come out of this whole mid-segment triangle things. The first one says that if you have 3 or more parallel lines intersecting 2 transversals, they cut the transversal proportionally. Parallel lines, 1, 2, 3. The transversal is that line that intersects them. And it's going to cut these transversals in proportion. That means this piece of this transversal in a ratio, in a fraction with this piece along that same transversal is going to be equal to a fraction made of this piece of the transversal, written as a fraction to this piece of the transversal. The second corollary is related to this one. This one is not proportional parts, but congruent parts. It says if 3 or more parallel lines cut off a congruent segment on a single transversal, then they're going to cut off congruent segments on every transversal. So if I get congruence here, I'm going to get congruence there. Not that these pieces from one transversal to another are congruent to each other, but along the same transversal, those pieces are congruent. So for skill practice question 9 through 10, it's going to look like this setup. I have 3 parallel lines. I have some transversals. Hey, I have some congruent pieces. I can immediately write an equation with those 2 pieces. Things that are congruent are equal, so I can just write an equation with those 2 pieces equal, solve that for the variable, and done. Well, what does that mean for the other transversal? Well, according to the corollary we just talked about, the fact that this transversal is cut into 2 equal pieces is going to imply that this transversal is also cut into 2 equal pieces. And so I can write this as my equation, solve for the variable, and I'm done. While I go ahead and write the solving for one of these, I'll take any questions on anything that you have. I'm watching the chat. I don't see any questions. I'm looking around the room. Don't see any questions. All right. If I don't have any questions coming in, I'm going to call today Dunzos. All right. That's it for us. Thank you very much for being here today. If you were part of the live studio audience, thank you for coming to school. We appreciate you. If you watch this on the recording after show on YouTube later, don't forget to leave me a like and a subscribe. Thank you very much. If you're one of my students, you can leave me a comment with a timestamp and a description of something here that helped you out. 1, so you can find it easier next time, and 2, so that I know that you're watching, and that'll help me out. I'll be able to put those timestamps in the description of each video, help others who are trying to find it. Thank you again. If you got any other questions, you're watching this on the YouTube, leave me a comment in the comment section below. Let me know what I was confusing about so I can fix it for later. Thanks again. Have a good one. Bye. Make some noise, 3B. Bye. Oh, applause? I get applause today? Cool. I'll take it.